Yeah, welcome back. It is my pleasure now to announce the second speaker of the day, Kalind Carpenter. He earned a Bachelor of Science in Industrial Design at Arizona State University and then a Master in Mechanical Engineering at Cal State LA, and he's now a robotics engineer in the Robotic Vehicles and Manipulation Group at JPL. And he's doing a lot of very, very relevant research for this particular topic of the challenge. He does a lot of work in rapid technology development and effectors tailored to gripping and rough surface mobility. He was also the co-inventor of the puffer that we have heard about before, and he does a lot of work on climbing robots, disaster relief robots like the RoboSimian concept. And he's also a mobility consultant and field engineer for another concept called the VOLCANOBot. And there is a special story about this lecture that I'm going to talk to you about afterwards. I don't want to steal more of his time, but remind me in case I forget. But for now, let's turn it over to Kalind, so please help me in welcoming him with a warm round of applause.
Excellent. Let's see if this is on. This will help. Excellent. All right, I think we're good. All right, my name is Kalind Carpenter. Thank you for the fantastic introduction. So I work on many, many technologies, but today, first I wanted to give you guys some background on Enceladus. I wanted to be aid you in your goal to accomplish what you're trying to do this week. And it's one that I admire a lot, having worked on similar kind of technologies. The distributed networks is a fantastic one, fast responses, and also the science that can be done on Enceladus, I think, is something we all agree on. Actually, Morgan Cable and I are working on a project that we'll go over at the end of this called EELS, the Exobiology Extant Life Surveyor. And so I think she's already introduced you to the science. So what I wanted to go over is, first of all, what do we know? Because there's a lot of things that's debated. This is a real image from Cassini, and we definitely can see there's plumes. From this, we know the mass flux that's coming out of it. We also know that the magnitude, the height stays about the same, even though the mass flux changes. So this gives us some interesting knowledge about what could be driving it, and that is probably converging, diverging nozzles reaching supersonic speed, so that the speed doesn't really change, even though the density is changing with the pressure, so the mass flux changes. The other things we know is the thermal gradient. So from the thermal gradient, we can actually bound how thick the ice is. So it's about 1 to 3 kilometers. So this is the stuff that is not debated. Almost everything else is debated. But when you're coming at a problem like this, you can bound the problem. And you can say, all right, let's just assume that all of these models have validity, and let's look at the envelope that means. What is it that we can take from this? So there's a bunch of things that could be driving this. You have your cryovolcanism, which is your shooken up soda bottle, right? And this is the best case for what you guys are working on, because this is going to carry the most out of the vents. So we know that there's H2, and we know there's CO2, and we know there's different volatiles. These things are going to come out solution, just like your soda bottle, before the water starts boiling from the vapor pressure. So this is going to be able to drive actual liquid out through the vent. So this is also the worst case for getting down the vents, but it is a very interesting case. There's other things. What if this is actually driven directly by heat? What if this is direct volcanism? What if this is the boiling method where you just have the vapor pressure of water and it's boiling because of the vacuum of space? What if it's just thermal sources causing sublimation of the ice? And that thermal source is causing a warm spot, the ice is sublimating, and that's what we see coming out. So there's a lot of things that could be going on. But we do know there's the 5 gigawatts of thermal emission. We know that there's salts in the E-ring, because Cassini flew right through it. We also know there's silica. We know, this is what he's talking about, the density changes, but the heights are unaffected. And this then has to do with the mass flux. So the mass flux is one of the things that helps us bound what could actually be going on with the vents. So it's interesting where we used to think a lot of it was CO2, and this was a very good sign for, potentially there being life. Now we know actually a lot of it's H2. This is in a sense more exciting for a couple of reasons. One, H2 is something that life can eat, so we have a food source that's right there. And then the only way you're going to get that out of the liquid water is with a very strong energy source. So this is probably being driven by at least serpentization or hydrothermal vents, but it's a better case for hydrothermal vents, meaning there's more energy in the system that could have driven things beyond a prebiotic state. So it's exciting information that's been coming out. We won't get too technical with some of this. The plume velocities, we know the gravity of Enceladus, we know things are reaching escape velocity. It's something that we can all agree is going on. So the fissures versus point sources. This is one of my favorite ones to think about. We know there's these 4 135 kilometer long tiger stripes, and each one of these is about 2 kilometers between these chasms that opened up. And we can all agree at some point this opened up between 1 and 4 million years ago. Well, in that time, you take this mass flux of 100 to 240 kilograms a second, and I calculated what it would take to actually fill these 4 chasms up, and it would be about 700,000 years. So being it hasn't been resurfaced before then, there's not much of a chance in my mind that this is your open fissure, but I'm an engineer. I work with sublimation gripping, and in the sublimation gripping, when I have the hot cartridges going into cryo ice, along the sides you see a sheaf form in real time of redeposition of this of the volatiles. So if this is going to happen anywhere you don't have enough energetics to actually get out, it makes sense to me that it's going to build up rather quickly to an evolved more point location. But both of them are fine. Like I said, they both have validity, and as an engineer, you design for both cases. So nothing answers all the variables we see. So none of these models is a clear favorite yet. Some of the things we do know: what happens with volcanism here on Earth where you have phase change? We know that it definitely does go to these circular conduits, even though it opens as a fissure. We can take some inferences from that they will probably circularize. As you get that phase change anywhere because of your no-slip conditions, or anywhere you're going to have an eddy or a backwater, you're going to lose your energetics, and it's going to freeze or solidify. And so that's probably going to go until the energetics of the plume pushes back on it. So if these are stable over a long enough period, it makes sense they would end up reaching their low energy states. The conduit could be straight, zigzag, winding, but not branching. I mean, there might be 2 branches, but you get too much, the energetics leave and everything freezes out. This also bounds the smaller sizes that you could have for some of the vents. The width is not constant. Similar to your rivers, anywhere you're going to have deposition and you're going to have sublimation and things are going to move back and forth, there is going to be change in the system. The dynamic changes in the vent. We know that there's tidal flexing. It's in a resonance, I believe, with Dione. So it's got Enceladus has a 33-hour day, and then Dione has a 66-hour day. So this is causing the pumping action, which we think is driving the energy in what's probably a fairly porous core. So this is also going to be flexing the ice. So this is going to be driving a lot of the energetics that we're seeing. Some people think or have said that everything closes up. Cassini never saw the plumes stop. So if the plumes have never stopped, we know that tidal flexing is definitely going to be flexing the tiger stripes. In an evolved case, if they've become cylinders, there's a good chance because they've been basically reinforced by that water vapor, and we know the rest of the surface is fairly porous by it having a different thermal gradient than it should have with liquid water 1 to 3 kilometers or even 10 kilometers away. So the only reason why we don't see more heat loss out of the planet would be if there's a pretty high porosity. So where there's the water vapor, it should fill in that porosity. So that's going to basically reinforce that area. So as everything moves, there's a chance that everything's just going around these. The other option is maybe it's just ablated away the sides. So even if it is these two open cliffs that are opening and closing, when they close, the plumes have ablated away the sides, leaving basically openings. Excellent. So the low mass flux means the vents are probably small. So they're probably around the 10 centimeter width. For you guys, this is less important unless you want to try to get down it. So here's the different models. So you've got your violent boiling just from your vapor pressure. You have your vapor under pressure. So this is the one where you have basically the lithostatic pressure is pushing in on everything because of the tidal flexing. That can be driving it. You could have your old salt-rich particles where this is just warm, and because of the composition of the ice that's causing sublimation, you could have your low salinity meltwater with just your slow boiling, or this is more your cryovolcanism version where it's coming out of a solution. That's what's driving the pressure. So when I was talking about the H2, well, some of the things this is telling us is there's a very good chance there's hydrothermal activity. And I don't know if you read the new paper that just came out by Lori Barge and Michael Russell and a whole lot, Caltech and other contributors. But basically, with a hydrothermal vent in an ocean where you have your rocky crust and you have your liquid ocean, right now that's the leading hypothesis for the driver of the genesis of life on Earth. So all you need is an ocean, rocky surface, and some hydrothermal activity. And basically you have a pH difference between the inside and the outside of the vent. That pH difference gives you a fuel cell. That gives you a constant current running for millions of years. Because you have the liquid all around it, you're going to have your potassiums and other things coming out of solution, depositing right there on the hydrothermal vent. You now have everything you need for your RNA and your DNA, and over time with those energetics there's this idea will drive self-replicating chemistry, and then at some point, we're not sure exactly how the energy gets in there to drive the transition to actually a metabolism. The way it was explained to me is you need enough energy to get that, to get your roller coaster up to the top. And once it's up to the top, then there's enough energetics to just keep that metabolism going as long as you keep feeding it. The other analogy that's been used is it's a scramjet. So if life's a scramjet that needs its oxidizer and its fuel, once it's going, it's very hungry. It wants to eat as much as it can. So you get something like this, you know that there's quite a bit for it to eat and a lot of energy around the hydrothermal vents. Where else do you think you would find the energy in the system for life, if there is life? Would you just comb through the whole ocean the same, or is there other places? The nice thing about a lot of these chemicals is they float. And actually, your proteins and other things will float. So the ice-water interface is another fantastic place to look. Also, if there is anything that's moving from the surface, in Europa, we know there's this almost plate tectonic movement. And we know that Io's been spewing all sorts of fantastic chemicals over the surface that's getting down into the ocean. That's why we really like Europa. That's why there's the Europa Clipper and hopefully the Europa lander. Enceladus, from an engineering perspective, is easier, and there's enough signs that it's definitely astrobiologically interesting, but we don't know what's in there because we don't know what's landing on the surface, and we don't know if there's mixing. But if there is mixing, once again, that's going to be in the ice-water interface. So the motivation, we know that contains organics. That's something Cassini did give us from flying through the Plumes. I do know that this is a little bit debated, not overly debated, but what else near Enceladus has organics that we know of? Titan, yeah? So Titan has this atmosphere, has tons of organics, and we've been flying close to Titan, and now we fly through the Enceladus plumes, and we find organics. There's some question as to if those are things that actually hitched a ride from Titan. But that being said, with Titan so close, there's definitely going to be some mixing. So maybe Titan is a really good case why things could be more interesting at Enceladus. It's definitely a good case for why we can get there and get into orbit. So these slides right here are basically looking at what could actually be coming out of these plumes. So let's say there is life, or it's a prebiotic ocean. What could actually be coming out of these plumes? So kind of the important things to get here is if you're flying through the plume, can you capture it? You know, you're all looking for the more heavy, interesting molecules that would come out earlier because they have more mass. So you probably want to land where you're actually going to capture them. But what happens when you smack into them? That's something people are finding out right now. How high do the interesting molecules and how many of them can you expect to find? This is some of the work that Chris Lindensmith has been doing. He allowed me to use these slides, which is really awesome. So here's your different models where you have your slow boiling, you have your cryovolcanism. So you can see in looking at these bubbles, this is probably going to carry quite a bit more. So you have film drops and you have jet drops. So everyone knows when you drop, you know, that famous picture of a raindrop on water, you know, you get that reverse raindrop that actually comes up. So you actually have this ability to get a drop leaving the body from kind of the physics of the bubble formation and the popping. In the slow boiling, you get a little bit of that, not nearly as much. But then what's going to actually be carrying it up, right? So the triple point boiling will give you both, but this froth is going to carry a lot more up to the surface. So this is a good illustration of kind of the formation of these drops. And this is what so much of what you're going to find on the surface hinges on, is the physics of droplet formation and the surface properties of the liquid that it's contained in. So this is actually a really interesting realm of study at the moment. Where is it? There we go. So this is something that happens on Earth. Why do you think scientists care on Earth about this phenomena? What do we not want to spread all around the planet? So diseases actually spread all around the planet by this. And the interesting thing about these ice clouds and everything else that's moving up, does anyone know how far our atmosphere extends?
45,000, 50,000 feet. Tropical ice.
Yes, but it actually has been found recently to extend further. Has a human ever left Earth's atmosphere? Or rephrase the question. No, human has never left Earth's atmosphere. So we know Earth's atmosphere goes around the moon, and the moon is littered with all sorts of detritus from Earth. It's actually, in my opinion, a great place to go looking for astrobiological specimens, even though we know where they came from, but we know that our sensors work if we can find them on the moon. If our atmosphere is extended out that far, solar winds, micrometeorites, things that aren't actually entering into our atmosphere but glancing through, are picking all of that up and actually spreading it all the way out as far as Saturn. So this is actually one of the ways that we know diseases move around Earth, but we also know things are getting picked up and carried even out of the atmosphere. And so for Enceladus, this is one of the reasons why we're very interested in the flybys and the landing missions. So we've done a bunch of experiments. Do you guys care as much about the experiments we've done and the results, or should we move on to some of the more technical areas for the surface of Enceladus and what you might find when you're trying to land there? Which one? Surface. That's what I thought. Excellent. So there's been some great lab tests where we then grow everything on Petri dishes. Find that you do find good stuff. All right, so mobility. What do we know about the surface? Well, fortunately, we have fairly good images of the surface of Enceladus. This is actually a DEM of the surface looking at the tiger stripes. So as you're coming in, you have this very kind of rough terrain. Globally, it's very smooth compared to most of the other bodies. But we have these deep chasms, these tiger stripes, and then unfortunately, we don't have a lot of information about what it looks like inside of these tiger stripes. But that's probably a pretty good area to land. As low points, there's a better chance that things will kind of cascade down to you if they don't land exactly where you're at. So some of the experiments that we ran to understand some of these properties is you have this liquid that's coming out at ballistic speeds, supersonic speeds, and that's going to freeze at some point. There's a lot of debate when it actually freezes. Does it freeze when it's still inside of the vents, or does it freeze upon exit? Does it need to have the radiation term without anything reflected back to it? If there is liquid, do you need to wait for everything to boil off? All of that aside, at some point it's freezing. We know the scale range from what Cassini's told us, at least at those heights. And so you can use an atomizer and spray liquid directly into liquid nitrogen. It's coming out at ballistic speeds. You're going to get these spheres. So that's a good way to do regolith. This actually just came out in this is a paper we just had published in the Journal of Field Robotics. So if you want to read more about this, this is, we did it probably about 4 years ago, but just got around to publishing. But I'm really happy we published it last week because now I can use it. So basically we ran all these tests where we also just ground up ice and then we sifted it to get the particles. And we did shear box tests inside of a thermal vac chamber to get the properties, the cohesion, the angular friction, and found that essentially it's above fly ash, but it's below sand. So it's like a very fine sand. So we actually tend to use silica spheres, hollow silica spheres. Turns out to be right in that range. So there's a couple mobility solutions we have to kind of solve how you get around on Enceladus. So one thing that I didn't really talk about is the cohesion you're going to get from sintering. So with this, even though it's 100th gravity, these particles fall back down. Is there enough energetics so that when they hit each other, they actually sinter together? You're going to get necking over time. There's not as much radiation as you have on Jupiter, which is a big particle accelerator, but there still is radiation, cosmic radiation over time. And what time scale are you going to have the sintering? At 100th gravity, does that sintered regolith or plume ejecta, does that bear weight? So there's some fantastic work being done for a landed sampling mission that we're looking at, because if you need to land and then sample, how are you going to react the forces of sampling the plume ejecta, or are you just going to wait for it to settle on you? The time scales, though, for the particles settling back down is, I've heard, as much as 1 million years for some of the smaller particles. But luckily, you're looking for the much heavier ones, which is great. So there's the different landed concepts, the different sampling concepts. One of my favorites that Gareth, who's going to be giving this talk, has been working on, and this came out of our Ocean Worlds mobility study that we worked on together, was this idea of ingesting the ice. And so you take your sample and you stick it inside over a radioisotope or some other heat source, and you have this ability to essentially, there we go, to hop around. You do this on plumes of basically water vapor that you've created. So you can take the regolith, shovel it in, and then you can do all of your analysis on it, and then you actually use it as your propellant. What's better than using, let's say, cold water vapor or using supercritical steam or all of the other things? You think of anything else you could capitalize off on something like this? What's rocket fuel, at least for NASA? Yeah. So if you have water ice, if you're turning it into liquid, if you can separate the bonds, you have some rocket fuel with a very high ISP. So here's a couple of the tests. I believe this is all just with your fairly cold water vapor, but it works quite nicely. So let's see. computer. That was fancy. Sorry. That's great. You can actually see the forces at the top as it's moving back and forth. So there's definitely some engineering challenges to make this work. But it's good to know that there's that much force. And then, is it going to go? There we go. So you can see, this is, in my mind, the Pixar solution. So this is how Eve gets around the planet, right? But let's go to some more traditional ways that you could do this. So currently we're working on RoboSimian. I kind of nicknamed this one Cryosimian. So by putting these mesh wheels on it, and I did build some out of Inconel, we basically needed something that could work in sulfuric acid ice if you were going to Europa, but it can also work on the evaporites that you see. So it actually is similar. If you do have enough radiation or enough energetics or enough heat coming through that you're going to sublimate the surface ice, what are you going to leave behind? We know there's saline in the ocean, right? And we know that there's this plume ejecta that could be carrying things with it. Is there a chance that the surface has this crust that has built up over time, similar to evaporites? So could we possibly land on something that looks like Devil's Golf Course, where my friend popped his Air Jordans and is not super hospitable? So this is one of those envelope cases. This is one of the worst cases. It's similar to the Penitentes case, but the Penitentes one's a little harder to believe. That takes more of your convection, which you're not going to see so much on an airless body, but you probably will see stuff like this. So RoboSimian gets around in this multimodality way where it can roll, it can walk, it can push roll, and it actually has a belly sled. So it can lay down on its belly sled to move itself around. So pretty soon we should actually know which of these is most efficient. So Enceladus awaits with its global ocean, unique chemistry, and internal heat. We know that it has the potential for life. If nothing else in the future for humans, it could be a big fish farm. We would like to get down. I probably shouldn't have said that, but you never know. Hopefully humanity is going to be around for a very long time. There's other concepts that I've been working on I want to introduce you to. So other than some of the surface applications, the one that I'm most working on right now is this exobiology extant life surveyor, which is more along the lines of what if you actually want to go down a vent? What if you do want to make it into the ocean, and we know that there are these open conduits that are being driven by a body of liquid? So there was this idea, why don't you just drop a ball down? And a tungsten ball in most of these plume models, gravity doesn't dominate, so it probably won't fall down. But if you had a rod of a given length, at some point it'll be long enough and dense enough to its projected area that it will be able to fall down, right? Even with the 100th gravity. So could you come up with something similar to that? Problem is I showed you guys that no one really believes these are straight. So if it's a rod, it's going to get cocked sideways and get stuck. But driven string of beads could probably do it. So we came up with this idea of landing right next to one of the vents and having a reconfigurable, adaptable, snake-like robot that is essentially a driven string of beads. So you have this thing that is, in the beginning, more of a mobile robotic arm for being able to get right to the plume to do its sampling directly from the vent opening. So from the vent opening, you know that the heavy molecules and chemicals are all going to be there. So this is a place to get your pristine samples. And we can also characterize what's going on. Once we know what's going on, we know, A, is anything relevant other than volatiles coming out of the vent, or do we need to go deeper? And so the idea of this is it can push onto the sidewalls, generate its own internal forces. So we know that over 4 meters, you can't, gravity actually dominates. So if it is over 4 meters, gravity dominates and you can fall. That's great. That's why I haven't been too worried about the open fissures. The more difficult one is if you've had this evolved case. So in this case, then it would start extending out, pushing against the sidewalls until it can become a self-driven screw. You have less mechanical disadvantage on each of the actuators pushing to the sidewalls, and you have a lot more areas which are in contact, essentially biting and cutting into the surface. We know that to have water vapor, even if you have a lot of salt in it, and actually in your water vapor case, it's not going to carry much of the salt with it. That's the problem. If you really want to know what's going on in the Enceladus oceans, you probably need to get to the water, because in the boiling or in the cryovolcanism, we don't know exactly the state of the sample once it comes out. So we know that the sidewalls are -10 to 0 C. So this is what you've ice skated on. This is the pole that if you stick your tongue to it, it freezes solid. There's a lot of things that we can actually capitalize off of that we use here on Earth that all of a sudden work as soon as you get into the vent system. Once you get through, all the models show that with the pumping action, the liquid comes up through these channels within 1 kilometer to tens of meters. So you actually don't even have to get down that far to be able to find the liquid water. But one of the problems is once you're in the liquid water, how do you react the forces from liquid? So the nice thing about these screws and Y screws is they're very bad propellers, not just gripping and kind of mobility wheel systems. But then in the end, the system can actually swim. So, not super well, but the nice thing about it is if we ever do get to go down to the hydrothermal vents, the hydrothermal vents tend to be these chimney structures. So you can't do station keeping very well, but once you get there, all you have to do is wrap yourself around. And now you can react the currents or any movement, and you have your sensors exactly where you want them to be. So right now what we're working on is an earth science version that we want to take to the poles to go up and down through ice sheets to get over the continents where you're going to have liquid water that doesn't run off. This is where we're finding really interesting life. This is where we can't see with radar. So being able to get down there, place sensor arrays to understand the changes over the seasons is great for climate science on Earth. Coming back up out of them, fighting gravity is actually similar forces to what you're going to get from the plume vents. So that's actually our planetary demonstration, is coming back out of the vent or out of the chasm. And then the goal is this will prove a possible technology for going to Enceladus, hopefully in the near term. Excellent. Any questions?